Welcome back to another lecture of differential equations. We're going to switch it up a bit and solve linear systems of differential equations. What? What? You can do that? Yes, you can. And this is very interesting. So, before we discuss about that, we are going to talk about first order systems. So even though we can do a systems of linear equations, our main focus will be first order systems. So in short, it is possible to take a higher order differential equation and convert it into a first order system. So a first order system looks something like this, where the functions f and g are equal to 0. Those are usually the homogeneous case, and it has a lot of variables. A solution for the system is a pair of functions of t that satisfy both equations over the same interval of t. So that's telling us that t is our only independent value, and we have other ones either being x or y, or in some cases it'll be x1, x2. And so how will we create this first order system? So if we want to create a first order system, let's start with something simple. So we're going to consider a system of second order, and this system of second order equation is as follows. So x1 double prime is equal to f1 of t, x1, x2, and x1 prime and x2 prime. And then x2 double prime is equal to f of 2 of t, x, x2, x1 prime, and x2. So to convert it to a first order system, we want to think of it of this system, we want to think of it as consisting of single nth order equations. So we will consider it as x to the n is equal to f of t times x prime times x double prime all the way to the x to the n minus 1 prime. And so now we can introduce these these dependent variables x1, x2, and x to the n. And so what we end up doing is we're gonna make x1 equal to x, and then we're gonna have x1 prime is equal to x2, and then x2 prime is equal to x3, then all the way to the x to the n minus 1 prime is going to be equal to x to the n, and then lastly our x to the n prime is going to be equal to our function of the first order system. And so this just becomes a nth first order equation. So it's going to be consisting of n equations, and they're all going to be first order. And so this system is equivalent to the original nth order equation in the sense that x of t is a solution if and only if the function defined satisfies the systems of equation. So as long as the system of equation that you create satisfies the original one, then they are the same. And so now let's look at a simple two-dimensional system. So we've known that the second order linear differential equation is in the form of x prime or x double prime plus p of x prime plus q of x is equal to 0. And we can transform that into a two-dimensional linear system if we let x prime is equal to y and x double prime equal to y prime. And so when we substitute that in, we're going to get x prime is equal to y and then y prime equaling to negative qx minus py. And so we know how to solve second order differential equations. So we can go back and forth with the first order system and the second order differential equations to find a solution. And so typically for what we're going to do is one, we have to make sure that p and x are constant coefficients and they're independent to t. But two, for this lecture, we're going to do examples where we get a a two-dimensional linear system and then transform it to a second order differential equation to solve them. There is a way to solve first order system, but that'll be more in the future. And since we have a linear system, if you remember back in linear algebra, we can use this system and convert it into matrix such that we can get x prime is equal to pt of x plus f of t. And these are all vectors, or some of these are column vectors and some of these are matrices. And so we can find a way to actually solve this using matrices. And again, this is going to be in a future lecture. So now let's just take it slow. So this is gonna be a really fun ride. So, okay, let's say we solve the linear system and we get a solution. So now what? So now we're going to discuss about the Wronskian of solutions. And since we can get a set of solutions, we need to verify if the solutions are linearly dependent from each other. And so that's where the Wronskian comes into play. So the Wronskian determinant can tell us if they are linearly dependent or independent. And to do that, well, let's find ourselves a set of solutions. So if we let x1, x2, x to the n to be solutions to a specific differential equation, then the Wronskian will be an n by n determinant. And these solutions are column vectors. And so all we have to do is just compute the determinant, and then whatever the answer will give us will tell us if they're linearly dependent or not. So if our Wronskian gives us 0, then the solutions are linearly dependent. Else, then the solutions are linearly independent. So as long as it's not equal to 0, they are linearly independent. And so that's pretty much it for this lecture. We're going to do a couple videos, obviously, about Wronskians, and then converting differential equations into first order systems, and then solving solving first order systems of 2 dimensions. So thank you guys for watching, and I'll see you in the Blackboard.